She's a professor of biomechanics at California State University, Fresno. She studies the physics of how animals and plants interact with water. 5 years ago, she started studying how bladderworts catch their prey by suction feeding. And the title of her speech is going to be Bladderwort Traps the Fastest Predators. I'm really looking forward to this one. So, thank you. Thank you. Try to get hooked up again. Hang in there. Okay.
So I'm the opposite of Larry in that I came to Bladderwort very, very recently. I've literally only worked on carnivorous plants for the last 5 years. So I'm terribly ignorant about carnivorous plants, but I know a little bit about flow because I've been doing fluid mechanics for the last 30 years. So I just want to thank Damon for inviting us, and we actually went through his carnivorous plant site in January and took lots and lots of pictures. So this is actually my research team. This is on the left side, this is Otto. In the middle, it's Max and Eshan. Eshan is my carnivorous plant expert, so I have somebody on the team who actually knows something about carnivorous plants. And Eshan has built me our little growing corner in our university greenhouse. So this is our little corner of carnivorous plants. It's mostly Utricularia, which is the species I work on, but when you order plants, they sometimes send you a few spare ones. And there's always volunteers. And so this is sort of the big tanks in which we keep the aquatic species. I try not to cause too many crazy sounds. So I work on bladderworts. This is sort of the pretty end, and bladderworts don't have a big problem of not eating their pollinators because business end and pleasure end are very different parts of the plant. So I study this part of the plant, which is underwater. I only study aquatic plants for now. And they make these little traps. They're in size anywhere between 0.5 millimeter and just under 1 centimeter. Yes, I'm a European, so I'm using millimeters for units. And when they are loaded, they look sort of flattened. And when they just caught something, they look sort of fat. Those plants they're more than 200 species, and the traps come in all kinds of shapes and sizes. I usually study the one that have very simple mouths, so I prefer things like Australis and Gibba. I stay away from the ones that have these ginormous afros because they're really difficult to work with. Because how we actually trigger them is we stick cat hairs in there. So I want to talk to you about how do they actually catch their prey. And biologists are fascinated about bladderwort, but they're actually the fastest predators. There's no predators that are faster. So they can catch their prey in less than a millisecond. And from a biology point of view, that is really weird. Because when you look at how long does a prey take to respond to a threat, it takes tenths of milliseconds. When you look how fast a bladderwort can catch their prey, it's less than a millisecond. And if you're a biologist, evolution doesn't do 10 times better than necessary. That's just not how evolution works. So why are these people so fast? So why are bladderworts 10 times faster than evolution needs to be? I put on there are some copepods that have what we call myelinated neurons. Neurons that have little insulation around them that makes them extra fast in their response time. So there are some copepods that can respond in 3 milliseconds. Everybody else, 10 to 20 milliseconds. Like I said, from an evolutionary point of view, it makes no sense that bladderwort are this fast when they catch their prey. And this is sort of where my research comes in. So the other thing that makes bladderwort really bizarre is the traps are really, really small. And like I said, I studied fluid mechanics for the last 30 years, and I have collaborators who study fluid mechanics as well. When you're small, that's a problem. We know a lot about how suction feeding works. What we know about suction feeding, we know from folks that are easy to study, large fish. So most research has been done on suction feeding in large fish. So what we know works great for large fish. Most of the research actually has been done on largemouth bass. I have next to them to scale what I'm studying, which is bladderwort and larval fish, much, much smaller. And when you're small and operating in water, that really matters. So this is sort of my Fluid Mechanics 101 for Carnivorous Plant Symposium. When you're really, really, really small, water behaves to you like really thick molasses, up to about the size of bladderwort or copepod. Water doesn't behave like you perceive water. When you're that small, water is essentially super, super viscous and sticky. It's like swimming in honey, living in honey. When you're very large, water is like water is to us. It's just wet and heavy, but it's not that sticky. So when you are very, very small, you build this layer of water that sticks to you, around you. When you're large, that layer of water, it's about 1 millimeter thick. It's negligible. You put a layer of millimeter of water around me, I don't care. I'm 1.50 meters. Make that 5'4". When you are 1 millimeter in size and you put 1 millimeter of water around me, you just tripled my size. And it's really hard for me to reach out of that. And I'll just show you some examples from fish larvae who are trying to reach out of this. This is the same size as a bladderwort in terms of business end, feeding end. And as you can see, having that layer of water around you pushes the food away. That is just the dumbest thing ever. And the other really annoying thing is that when you're very small, flow is reversible. So if you do the same motion one way and then again the same motion backward, flow reverses. So yeah, you sucked it in, awesome, and you spit it right back out. So that's the problems you're facing when you're small in water. That's the effects of viscosity. And it really messes feeding up. So I have a collaborator in Israel who studies suction feeding in fish larvae, and he found that when the larvae are still very small, but these viscous effects are important, their feeding success is really poor. And as they get older and bigger, their feeding success gets much better. And yes, it's not learning. He's actually put the big larvae into water that he added wallpaper glue to, so it gets more viscous again, and their feeding success goes right back down to when they were small. So it's not learning, it is fluid mechanics. So then my research is essentially, what do plants know that fish don't? Because my bladderworts can do this trick just fine, where fish larvae fail miserably. And yes, you could say, dumb fish, they should just put a door in front of their mouth, just like the bladderworts do. It's problem solved. But it's not as simple as that, because the bladderwort can do it even without the door. So my question is, how do small suction feeders overcome the headaches imposed by being small, and therefore by operating in viscous flow? Like I said, I'm a fluid mechanicist. If I go way over your head and I use words that you find intimidating or explain things in a bad way, do interrupt me. So again, we're doing a bit of fluid mechanics 101. So suction feeding is essentially, you do suction feed constantly for the time being because you're trying to forbid straws because they're bad for the environment. But for the time being, while you're still sucking, so drinking through straws is essentially suction feeding. And when you are trying to experience what it's like to be a fish larvae or a bladderwort, think about drinking through a really, really simple little cocktail straw, drinking honey. So when flow is viscous, it's just looking like this. The water essentially blocks the straw. When you enter the straw, you see that the flow profile is still quite wide. What you see in gray is called the boundary layer. So water, when it first enters the straw, it still needs time to realize, hey, there's a surface area, I need to stick to this. It's called the boundary layer. Boundary layers take time to build up. and they take space to build up. So in the beginning of a suck, or at the entrance of a sucking object, your boundary layer is really thin, and you effectively, like viscosity doesn't matter. As time goes on, or as you go deeper into the straw, the boundary layer gets thicker and thicker and thicker until it reaches the thickness that it's comfortable at, which is around 1 millimeter. And then you have fully developed flow. If your straw is thinner than 1 millimeter, you've effectively blocked your straw. Does that make sense? If you have a big straw, you can suck through the straw. That's why when you go to a restaurant, they don't give you a straw that's thinner than 1 millimeter in size, because that wouldn't suck. But so that's sort of the physics behind it, that you can have effectively viscous flow by having a very narrow straw, by sucking for a long time, or by sucking through a long straw. I work with people who do what's called computation fluid mechanics. It's getting a bit scary. And we just calculate what would the flow look like if you were sucking. And we calculated this for inviscid flow and for viscous flow. If you look at this, can you see how this is a much more square velocity profile, and this is a much more of this curvy velocity profile. Can you see that? So this is a bit flatter, inviscid. This is viscous flow. We did this by making this straw really wide, 1 millimeter wide, just above 1 millimeter, which is the magic number to not block your own straw. If you make it 10 times smaller, the flow goes viscous. Here, red means maximum flow speed in this picture. If I normalize it as absolute values, the flow speeds here are essentially negligible. So this previous picture is, the red is the highest flow in that picture. Here, it's what's red here would be red here. So now it's the same absolute scale. As you can see, when you get very small, there is no water flowing into your mouth, what you saw in the fish larvae. So I explained to you that if you don't give water time to build a boundary layer, you might just get around this. So perhaps that's why Bladderwort are fast. If you're really, really fast, you simply beat the water to becoming viscous. Perhaps that's our explanation why you're so fast. They're not trying to outwit the prey. They're trying to beat the water. Sounded like a brilliant idea. I wrote a grant proposal. They actually gave me money to do this. Couldn't believe it. And you can already see that now coming. So we had this brilliant idea. They're fast to beat the water. So we went, okay, we know what flow should look like if there's no viscosity. We know what flow should look like if there is a lot of viscosity. Here comes the scary math. Fluid mechanics is actually scary math. So we have equations for viscous flow. We have equations for inviscid flow. Don't worry about the equations. If you solve them, this is what this looks like. I'm calculating what should the flow into the bladder look like. This is distance from the mouth. The mouth is here. And on the y-axis, you see flow speed. Of course, the speed is highest right next to the mouth, and as you get away from the mouth, the speed gets less and less. If you compare the two models, you can see this one, the speeds are much lower, but they take much longer to peter out. So they last much further away from the mouth. Here, you have high speeds, but they peter out faster. So we have beautiful predictions. What did the Bladderwort do? So we actually have high-speed videos. We're filming at 50,000 pictures per second, because I told you it goes really fast. There's our camera. Then there's our specimen. And we're filming what this flow looks like. And then this is sort of a typical flow field. So we put little particles in the water, because water is transparent, I can't see it. So we put little particles in, and then we can trace the particles. We artificially triggered the bladders by using eyebrows from our cat. I don't rip those out. I just collect them whenever we hoover and we find one. So these are all voluntary donations. I want to emphasize this. So my cat is part of our research. Everybody contributes in our family. When we now compare what I find with what I predict, can you see how what the bladderworts are doing is essentially inviscid flow? So awesome. You're really, really small, and fluid mechanics predicts you should be viscous flow, but in reality, you're actually inviscid flow. So that's good. Just some silly facts. When I say these guys are amazing, I mean that. The accelerations are 5,000 Gs. That's insanity. Humans faint at 10 G, by the way. So if you accelerate a human at that, you're just essentially jammed. Yeah. So they make amazing accelerations, and they get also very high flow speeds. These flow speeds are typical of a largemouth bass. So they're really amazing, folks. And this is sort of what the experiments look like. We sort of trace the particles into the mouth, and you can see the cat hair coming up. So, conclusion is, yes, the flow is inviscid despite their small size. How do we keep the flow inviscid? Like I said, we were hoping that it's developing flow. Developing flow means the flow isn't ready yet. The boundary layer hasn't formed yet. It's developing. And our null hypothesis is, because as a real scientist, you always need to have a hypothesis, and then you need to have your, what's the other explanation? No, there simply are actually in normal inertial flow by some other magic. We just don't know how. But we were hoping it's developing flow, because that would be so nice. I already explained to you that there is, like I said, inertial flow is something you could generate. If you make a high pressure, if you suck really hard, you can probably get to simply inertial flow regime. Like I said, that would be the boring explanation. We were sort of hoping that we're trying to explain why are you so fast. So we were hoping to find it's that startup effect. The boundary layer still has to develop. It hasn't developed yet. Let's see whether it's that. There's also the entrance effect. Remember I told you it takes time for flow to develop along the drinking straw. If you keep your drinking straw really short, again, you don't have a boundary layer. Does that make sense? So these two hypotheses have to do with developing flow ideas, which would be sexy. We were sort of hoping it wasn't the pressure. So we're testing through the hypotheses. Again, we do this with computations, and we just simply plug in numbers that are typical for bladderwort, and then we plug in numbers that are typical for fish lorry, and then we do some cases in between. And what you can see is, if you look at the velocity profiles here, you can see that's a flat profile. If you look at the velocity profile here, you can see it's a parabolic profile. That was viscous flow, and that was inertial flow. We did simulations where we're looking at startup effect. Does time matter? Remember, that's what I was hoping would be true, because then I finally have an explanation why are bladderworts so fast, which we can't explain from a prey interaction point of view. So not working out. So we looked at what does the flow look like when I give it the whole day to develop. And what does the flow look like after 50 microseconds? And this is inside the bladder. This is inside the drinking straw of the bladder. This is outside. Outside is the only thing that matters, because that's where you catch your prey. What's inside is not interesting. Everybody agrees? Does that make sense? Because what's inside, the prey is already gone. You already caught the prey. The only thing that matters is are there differences outside, because that's what catches the prey. And as you can see, there's no differences outside. So our brilliant idea that we got money for didn't work. I haven't told the funding agency yet. The money officially ran out this summer. Now I have to confess. The brilliant idea didn't work. Entrance effect. So that's the, if I make the straw really, really short, does that help too? And what we found there is, if you make the straw really short, you do get a brief boost in velocity. So this is time, this is flow rate, and as you can see, if you make a short straw, you get higher flow rate sooner, which is a good thing to catch prey. This is again computational values. This is the actual experimental values from the flow, from the bladders. As you can see, the drinking straw, the functional length of the drinking straw is essentially 0. So that little opening area of the bladder is functionally very, very short. This is a complicated slide. The main message is we measured through the entire parameter space. From, at this end, fish take about 10 milliseconds to go from opening their mouths to peak flow speed. At this end, we have the crazy speeds that Bladderwort are capable of. When you look at the lines from the bottom to the top, the bottom is pressures that fish larvae can generate. The tops are pressures that Bladderwort and adult fish can generate. What you can see is essentially, if we look at the time frames that bladders do and the pressures, they are super fast. Our predictions match our data. This is just science talk. This is the easy summary. So we have these 3 ideas. High pressure matters, being very fast starting up matters, having a short drinking straw matters. Matters either to get things started quickly or to make the water flow really, really fast. Both are important. You want to have high flow speeds so that you can entrain the prey. You want fast onset so the prey can't get away. The only thing that gives us both is the high pressure. The whole startup idea for completely flat, the entrance effect gives us briefly faster flow. It does give us faster onset. So that was us testing our hypotheses. Remember, our main hypothesis, developing flow matters. The null hypothesis was inertial flow matters. And unfortunately, we have to conclude that the high pressure is the biggest story. So it's really, really important that bladderworts are capable of generating these extremely high pressures. And this is sort of where I'm working with the person who was supposed to be here today, Simon Poppinger, because I'm just the stand-in. The only thing we share is we both have a German accent. And Simon is going to help me look at what amazing materials are bladderworts using so that they can generate these extremely high pressures. Because their bladders are just a few cell layers thick, yet they generate pressures that are similar to the pressures that we measured in largemouth bass. So there's these stinky little structures, and they can still generate amazing pressures. Okay, we now figured out that what I was hoping for wasn't the answer, but the question is still, so you can make this amazing inviscid flow that starts really fast. Is that doing any good? Because I showed you that fish larvae are terrible at catching prey. You would think that a bladderwort should be better. So these are our numbers from our bladderworts. We actually put bladderworts into mason jars with prey, and we just call them death matches. So we put them in there for 2 days, and look what happens. And what we found is that there is a decent fraction of bladders that catch prey, and it takes a few nodes before bladder is ready. So this is for Australis. So the youngest nodes simply are not mature yet. The bladders don't catch anything yet. From node 5 on, you see a steep increase in prey capture. Then the bladders are really happy, and then we get a bit of senescence. But most of the senescence is actually bladder simply falling off, and then the bladder stopping to catch. The capture rates are not that much better than fish. But it's a really apples and oranges comparison. Because a fish has just one mouth. Australis has hundreds of mouths. Fish catch food for energy. Bladderworts catch food for nutrients. It's a completely different story. You don't eat as much vitamins as you eat calories. So they're doing this for very different reasons. And that's important to keep in mind. Plus, like I said, one mouth versus hundreds of mouths. If just a few of my mouths are successful, I still ate a lot of food. as an individual. Just a few more things just from my master students. So this, what I just shared, part of it is work from Max. He found that 50% of all the captures actually occur on a third of the nodes. So there's just a few, but it's a highly, highly successful. It also important is we have a lot of spontaneous fires. Traps don't just fire because prey touches the traps. Lots of traps fire spontaneously. We have just as many fires in mason jars without prey as we have in mason jars with prey. And we're not smoking too much legal weed. We have a method where we actually put fluorescent dye into the water so we know exactly who went and how often, because the more often you go, the higher concentration the dye in your belly. And we see dyed bladders just fine without the food. Small traps make up the majority of the energetic cost because they fire a lot spontaneously. So small traps cost a lot of energy because you have to pump the water, yet they catch hardly anything. We do know that when they get triggered by prey, they have a very high success rate. So that's Matt's work, that's the guy here. We know that usually when prey triggers, the prey gets caught. So they know that the success rate that way is high. But we also know that traps essentially don't catch small prey. So they catch medium-sized prey, but the smallest prey they simply ignore. That's another silly thing we found. So we have a very high of spontaneous or misfiring, which costs a lot of energy. The question is, why would you do that? And we have a lot of small traps that do a lot of spontaneous firing. They don't catch a lot. They catch very little. So those are sort of the remaining mysteries that we're going to change after in the future. I just want to thank my collaborators in Japan, in the Netherlands, in Israel, and at home. And that was me. Thank you.
Regarding the spontaneous firing, I'm sure you're familiar with Simon Pinker's explanation for this, that it avoids material damage because they're continuously pumping out water, so they have to release, they have to trigger the trap from time to time and recreate this pressure.
Yes.
But my question to you was, from an evolutionary perspective, I'm always fascinated that there's a size limit for uticularia traps, which is below 2 centimeters, so they don't get bigger. And it's not about the restriction of the prey size. There would be not like. Is it about the velocity method that you can't create a super large uticularia trap, or is it material?
I think it's material because it's very easy to be strong and small. You know how hard it is to squash a tick when you're trying to kill a tick? That's really hard. Squashing a big buck is much easier. So just from a material point of view, it's much easier to be strong and small than to be large and strong. So I think the utricularia, that energy storage doesn't work. But Simon also told me that there's one species of utricularia with passive traps.
Yes.
So, and to my knowledge, they're large.
They're quite large, but also some species, there's always quite traps that get really large. There are minor traps, almost 2 centimeters.
Yeah.
Utricularia volvii and some of the Australian species. The rest of the species have smaller traps.
Yeah.
But they fully function also as large.
Yeah.
So it's not velocity matters.
Because I don't know, because the other thing that worries me is what I call the afro. You know, you have some traps that have these ginormous constructions in front of them, and we try to work with those, and we can't even get particles near.
Yeah, Simon and I were working on this. The rest of the species have these
the afro,
structures in front. And our explanation is that these, because they're in a terrestrial environment, and what these structures do, they capillary capture water. So in the drier environment, they always have water down, so that they don't not run dry when they do this spontaneous firing. They also do the spontaneous firing, but they always have a water bubble, and they recreate this water bubble in front of the trapdoor.
Because what I find surprising is that I cannot get objects into their mouths.
Yes, and they have a very long tunnel in front of us.
They do. And they don't have a round mouth, they have a slit, which from a fluid mechanics point of view is completely different. Yeah.
So this would be from the fluid mechanics would be very.
Yeah, and like I said, for me as a fluid mechanicist, nothing what they do makes sense. So it's just like, you do want the worst thing possible. Having a slit, I mean, just flatten your drinking straw and try to drink through it now. That is just about the dumbest thing ever. You're literally stopping yourself from drinking. I mean, it's just, it's just mind-blowingly dumb. They're doing it. So it clearly makes sense to the plants. We just haven't figured out yet why it makes sense. Yeah. Shoot. Which one? The water wheels. I stay clear of the water wheels because that's Anna's territory, which is Simon's PhD student. So yes, they have looked at they started at the they're at the mechanical side now, the solid mechanics. So they now have a good solid mechanical model of it. But because they don't reset, it's a whole different story anyway. Remember? So to me, they're so different because the mechanism is very different because like underwater Venus flytraps, and they don't reset. So there's all kinds of things that are sort of fundamentally quite different, including opportunity costs. Because if you can't reset, that's a real. You better be very careful that you don't go off without a purpose.
I know Anna's work. They have shown that they are not as successful with having as they sometimes pushing out and spraying with the water.
Yeah, because that snapping mechanism, again, that's the flow bites you. When you're that small and you use that mechanism, the boundary layer pushes the water away from you. And it's again, what were you thinking from a fluid mechanics point of view? So.
Has it been ruled out that the antibiotics secrete small molecules alter the water behavior in either inside the craft or in the immediate vicinity of the craft? Because, of course, that would be an available evolutionary strategy that you could use, but I mean, I don't know.
I said, I'm not the chemist kind of person. I thought they do excrete stuff, but I'm not sure. What I do know is that we were sort of worried about, is it just a microbiome, or are you actually getting benefits from the prey you're catching? Or are you like a cow, where you're eating food, and then the microbiome in your belly digests it, and then you're actually eating what the bacteria make, and the prey are not for you, but they're for the bacteria in your belly. And we have some preliminary data that they can take up large amino acids. So it looks like they can take up prey. But I don't know how they attract prey, or whether they secrete prey. Secrete goodies for the prey.
But the question could have been this: can they break the no slit condition by chemical modification?
Oh, can they break the? Oh, now I get it. Like fish slime. Sorry, I'm slow. And I wouldn't have expected this to work. I mean, again, because it's over in 0.5 milliseconds, you usually don't use no-slip slime because what for? It makes no difference. You're already in an inviscid flow. So I don't see how the slime would help. Sorry that I misunderstood your question.
Well, I wasn't basically the slime per se. I mean,
Yeah.
there are lots of ways that small molecules can water behavior.
Yeah,
and,
it's true.
Particularly if you're trying to small scale. So I'm just curious whether or not there was any form of that was active or not. But
Yeah.
it's really.
Yeah, I would say it's not necessary because in our mathematical models where we assume nothing, they already achieve inviscid flow. So why fix something that isn't broken? Yeah. I saw a hand in the back, but I forgot.
Yeah, it kind of relates to that. With slime, I always think about Newtonian fluids and so mixing that with water when you're suffocating,
Yeah.
you end up with something shear thinning, which will obviously help you to get through that small opening.
Yeah.
So I was wondering if you can sample the water from freshly fired traps and measure their viscoelastic properties and
yeah.
see whether you have an alteration to what you find in the pure water.
But again, we have these mathematical models that show we don't even need that. We already have implicit flow conditions without that. But yes,
But you could have it even though you might not need it. So
But then
you might add
again-
something to your story.
in the sense of now there's even more confounding factors that we can't explain. Yes. There's lots of questions. I go then you.
Since you mentioned that the trap size or show variations in the amount of prey they caught and the differences in how much the traps misfired, did you observe those differences just in like younger and older traps on the same species or across species? Since I would be curious whether prey availability and the possibility of misfiring would be selective pressures for the development of different trap sizes in different species of the different area.
We have only studied this in 2 species so far. So we've only done it for Giba and Australis. So I haven't done a big cross-species comparison yet. We just stuck with a vulgaris type traps because they're nice and simple. And they're also similar in size because we're using prey that, according to other papers, is sort of neutral to favored rather than a species that from field data looks unfavored. So what we haven't done yet is lots of different species of prey and lots of different species of predator. Because indeed, like you said, that would be interesting to do next, but that's for the next master students.
Australis itself produces a range of mature trap sizes.
Yes.
And that's total mystery.
Yeah, we have, Australis has a wide range of trap sizes, from 0.5 to about 2.7. This question and then there.
Yeah, what are the peak flows that you're measuring?
Yeah.
How high are they?
In the straw, in the drinking straw, 5 meters per second. Fast. Outside of the mouth, closer to 0.2, 0.3 meters per second.
Are there other examples of higher speeds than that in other biological systems? Because that's very, very fast.
Yes, like I said, adult fish.
We'll go that fast.
Yes, but fish larvae, 1,000 times slower. So something that's the same size is 1,000 times slower. But something that is 1,000 times larger is like a bladderwort. That's sort of one of the puzzles. Why would they do that? Sure.
What would be like a technological sort of application of this, or like I guess I'm asking for your funders. What does this? How could this be used?
The people who are most interested in this is microfluidics, so microinjections. So whenever you're trying to manipulate flow, very small flow, then that becomes interesting. So microfluidics is a big deal, not just for inkjet printers.
Right. Okay. Awesome.
Yeah. Thank you, guys.